Hello, this is Math 280 Multivariable Calculus. I'm Professor Wheatley. Today our topic will be the unit binomial vector and some talk about acceleration. This will be the last of our 3 lectures on some differential geometry and sort of how things move in 3 space. So let's start with point P on space curve R of t. So at this point P, we have unit tangent and unit normal, and we know unit tangent points in the direction of motion and unit normal points in the direction of curvature. So these 2 vectors are orthogonal to each other. They form a plane. We can talk about what the vector normal to that plane is, because these 2 vectors are in the plane. Right? So T and N form a plane, and we could talk about B, the unit binormal vector, is the right-handed unit vector perpendicular to this plane. That is to say, it is cross product of T and N, right? So B is T cross N. So let's draw a picture here. Here is space, right? And you've got some space curve. Maybe it looks like that. And maybe down here is some base point, right? And over here is some point P, right? Let's put P down here. And maybe T points like that. So maybe that's T, right? And N is orthogonal to T, so maybe N is sort of pointing like that, right? And then B points up and out of that plane. So wherever this plane is, there's something pointing out of it in the right-handed direction. So this angle is going to go counterclockwise. So that means that we're looking at B pointing sort of out of, if the board is here and we're moving from T to N like this, B is pointing out that way. That's the right-hand rule. So maybe our B sort of looks like that. That's kind of 3D looking, right? So, and then you get that's right angle, and that is a right angle there too. So you get this plane formed by T and N, and B sticks out of it in the way the right-hand rule says it does. Right? So these vectors form sort of a moving frame. So they form a right-handed frame, and it is a TNB frame, Frenet frame sometimes also called, right? And this frame moves with the points. In other words, at every point on the space curve, it's a different frame. T is different. As a consequence, N is different, and so as a consequence, their cross product is different. So you can imagine as you move along this curve, you have this frame constantly moving with you, and it's always right-handed in the sense that B is by the right-hand rule, right? So these are mutually orthogonal. They're all orthogonal to each other. That is to say, any pair of them is orthogonal, mutually orthogonal vectors. Unit vectors, actually, mutually orthogonal unit vectors at each point P on this space curve, right? So that's the TNB frame. Okay, so that's sort of the broad global picture. Let's zoom in now on this point. So let's zoom in on point P. Zoom in on P. And then what do we see here? So here's P. And what we get, so this is T, this is N, and that's b. So this looks a lot like 3-space, right? I mean, 3-space is the same. I mean, over here, didn't label these, but this is x, y, and z over here, right? So that's our usual 3-space picture. That is the picture at P. So this looks just like a copy of 3-space. 3-space is made up of mutually orthogonal vectors, ij and k, lines through those vectors. Here we have the exact same thing, right? And these are all mutually orthogonal. So let's see if we can make these look reasonably decent, right? And there, so there's mutually orthogonal there, right? And so this actually forms 3 planes, just like space does. Space forms xy, yz, xz. This forms planes formed by TB, BN, and TN, and they have names. So the plane formed by T and B is rectifying. So the rectifying plane. The plane formed by N and B is the normal plane, and down here in T and N you have what's called the osculating plane. The osculating plane. Right, so those are the 3 planes determined by T, N, and B at any point, right? And it turns out that the osculating plane is sort of it's the plane that comes closest to containing the parts of the curve near P. In other words, so the osculating plane is very similar to a tangent plane in a lot of ways, or the idea of it. We haven't really covered tangent planes quite yet, but if you think about it, the tangent line for a function of one variable was the line that best approximated the curve at a given point. The osculating plane certainly contains the point P, but the curve P is closest to this plane. In other words, if you were to sort of walk on this plane, you would be as close to the curve P as you could be for any plane that hits that curve there. This is the best. So in other words, distance-wise, at least, you are closest to having this curve P down in the osculating plane. All right, so let's do some analytics here, get some of the equations for these guys. We know a lot about the equations of planes from our earlier work. So these guys are just planes. We know the vectors that make them up, and so getting their equations, as long as these vectors are manageable to work with, is not a terrible thing. So suppose we had a nice, easy helix. Right, helices are nice because they have nice, easy T and N's, as opposed to things that can get pretty nasty if you let your space curve be any old thing, right? Let's talk about that space curve at this point. Let's look at the osculating plane. Let's look at the osculating plane. Okay, so we need T and N, and then we'll cross them to get B, and that will give us our normal vector. We have a point when we plug in this point, and then we just go to the plane equation. So let's go to it. So T, remember, is V over length of V, right? So V is 3 cosine T I minus 3 sine T J plus K, right? Length of this guy, if you square those, you get a 9 sine squared and a 9 cosine squared. That leaves you with a 9. And this adds a 1 on there, and the square root of that is square root 10. So I won't go through the details here, but you get that thing, right? And you can break this up into components if you want to, right? Maybe we'll do that just to be. So 3 over root 10 cos T I minus 3 over root 10 sine T J plus 3 over root 10 K, right? Now I need N, right? n is t prime over the length of t prime, right? So t prime winds up being minus 3 over root 10 sine ti. This ends up being minus 3 over root 10 cosine tj. And the k term zeroes out. It's a constant, so its derivative is 0, right? And if you look at the length of this thing, right, this ends up being, what, 9 over 10, and this is also 9 over 10, and then you have a sine squared and a cosine squared term. They don't do anything, right? So we wind up with square root of 9 over square root of 10, which is 3 over root 10, right? So the length of this thing is 3 over root 10, which is great because these just cancel out, right? So this winds up being minus sine ti minus cosine tj, like that. So there's your n. So there's your t and your n that form the osculating plane. Now what we need is unit binormal. We need the cross product. And so sort of a useful shortcut is if you don't want to deal with ugly functions in the cross product, and usually you don't, what we really care about here is just the osculating plane in a single point, right? We don't want some general expression for it necessarily. So I can just figure out what t at that point and n at that point are, and then cross those two vectors, and I'll get a valid b. So t of pi, and if I plug in pi, there's t, right? The cosine term becomes negative 3 over root 10 I. The sine term disappears, and we get 3 over root 10 k. That's t of pi. And n of pi, right? The I term is 0 because pi, sine of pi is 0. The j term is negative cosine of pi, which is negative 1, which is positive 1. So n of pi is just j, right? I have, okay, so I've got to back up here a minute. Make a small change to your, if you're working along with me here, I've made an error. This should be 1 over root 10. So this is just a 1 here. So that should not be 3 over root 10. It's just 1 over root 10. So no 3 up there. So make that adjustment. Didn't matter for n because this went away anyway, but it will matter here. So if I want b of pi, it is a t of pi cross n of pi, right? So I set up my usual cross product determinant, right? Have coefficients here, 3 over root 10, 0, 3 over root 10, 0, 1, and 0, right? I can do my usual cross product. So the I component is minus 3 over root 10 I. The j component is actually 0 here because that cancels with that, right? The k component ends up being minus 3 over root 10 k. This is what I have here. Oh, I see my problem. I made the same mistake twice. So all right, I corrected it once over here, but corrected over here. This is 1 over root 10. 1 over root 10. This is 1 over root 10. So this is 1 over root 10. Okay, now we're in good shape. So everything through here has been 1 over root 10. We've corrected that all the way through. This is the correct cross product that we want. So b is normal to this guy, where it's coming out of the osculating plane. So the vector negative 1 over root 10, 0, negative 3 over root 10, right, is a normal vector. Normal vector to the osculating plane. Right. And I need a point on the plane. Well, r of pi will do nicely. So r of pi, right, winds up being 0, minus 3, and a pi. Let me make sure I think that that is correct here. Yes, I do. So this is a point on the plane. So this is point on osculating plane. Right? And the equation is going to be these coefficients. So you've really got something that looks like there's your usual plane equation where your A, B, and C are your coefficients of your normal vector, and these points are from there, right? So this winds up being negative 1 over root 10 x, and then this whole term is junked out, and minus 3 over root 10 z, and then it ends up being a minus pi here, so you wind up with this, this extra piece, which is positive 3 pi over root 10 equals to 0, like that. And then the root 10s can be cleansed out, and actually you can put through a minus 1 if you want to. And this ends up being x minus 3z equals 3 pi. And is that what I have here? Yes, it is what I have here. OK, good. That looks good. So there is your osculating plane. There is your osculating plane, right? OK. So you could find the equations of rectifying and normal planes very similarly. There's almost no difference in doing that. In fact, it's probably actually shorter because, for example, if you wanted to find the normal plane, the vector that is normal to the normal plane is unit tangent vector, right? So t. So you'd only really need t to get that, and then a point in the plane, and then you have your normal plane that way. The same thing if you wanted rectifying, you would use n as your normal vector, so you may need actually less. So really osculating probably requires the most work, but it's also the most widely used. All right, let me shift gears a minute here and talk some about acceleration. I think this is a worthwhile thing to explore because it does have some nice applications or some nice intuition that follows from some real physics here. So let's talk about acceleration for a bit. Right. Acceleration in space has two components. Right. One in the direction of motion, i.e., one part of acceleration points the same way that t does. So one point the same way t does. And one in the direction of curvature, i.e. one points the same way n points. Right? OK. So how are we going to approach this here? A few things to take note of. First of all, we know that unit tangent is v over length v, and we can rearrange this a little bit to get v equals t times length v, right? And we also remember that length v was speed, right? Well, we have this little equation v equals t times length v. We know that if we differentiate velocity, we get acceleration. So if I differentiate both sides of this, I will get on the one side acceleration, on the other side I will get something that may be useful to me. So let's go ahead and do this. So let's differentiate both sides of the above equation. Right? The one side is just v prime, which is a. Right? The other side requires product rule. These are both functions of time, so I have to use product rule on this. Right? So this is t prime length v plus t length of v prime, right? Notice this is not This is not length of v prime, it's length of v prime. So this prime is outside the magnitude operator. All right, what else can we say about this here? Let's get curvature involved. So similarly, let's get curvature involved. Remember that curvature, we defined it as length of t prime over length of v, right? So this was from last section. And let's move some things around so we can solve for length of t prime, and that's curvature length of v, right? Furthermore, so this is sort of one thing to take note of. There's one. Also taking note of the fact that the unit normal vector is t prime over the length of t prime, right? So the length of t, so what does this tell us here? It tells us that t prime is n times the length of t prime. All right, that's moving this around. And length of t prime is this guy up here, right? So that, I guess I wanted to use an arrow here, didn't I? T prime is n, let me say it this way. It is curvature length of v times n, like that, right? So constant times n. In other words, it points the same direction n does. It makes sense. T prime is just the same direction n is, only it's normalized by a length, right? Okay, so what that means is that there's two pieces to acceleration. Let me come over here. So one piece is just straight length of v prime times t. That's this guy right here, right? He's just getting moved over there. Right? This guy is right there. This other guy was involving t prime, but now I've gotten t prime to the point where I got it in terms of n, right? So now I can say this is plus k length of v n, right? And in fact, it is actually length of v squared, because this is also a length of v here. So there we go. So this is length of v squared, and let me move this slightly. Right? So what did I do here? I took this guy and replaced t prime with this, and I wound up with curvature times v, length of v times length of v again, and that is all scaling n. So there is something about A, and we can see that we've broken it down now into a component in the direction of t and a component in the direction of n. There's the t component. There is the n component. This is what we call the tangential component, right, in the direction of unit tangent. And this is the normal component. And actually, I'm sort of being slapped with what I'm writing here, but it's really just the constant part that's called a normal component. The normal component. Right, so tangential component, normal component. Makes sense. And so we can abbreviate this as sort of a sub t times t plus a sub n times n. Right, so this is the tangential component. This is the normal component here. I want to spend one more minute talking about maybe a simpler way to get the normal component here, but let's take a look. So let me get rid of almost everything. Just this, actually, I'll get rid of. All right, so let's do a brief note over here. We know that the length of a squared is a dot a. We know that's true for any vector. So we have that, right? And I have a now written in terms of this at and an. Maybe I'd like to try to get an in terms of at and a. That would be sort of helpful, but not necessarily required, but it's still a nice little thing to do. So this is att plus ann dot att plus ann, like that, right? So that's just a dot a, and just written in expanded form down here, right? And so we can do literally a foiling here, right? In other words, what we have here is at squared times length of t squared, right? So this is literally that times that, that times that. So it's just FOIL. It's the typical FOIL applied to just constants on vectors. And you could check out and see that this is in fact true. This does work for vectors. And then what do we end up with here? We end up with a 2ATAN term, and then the vector that hangs around there is t dot n, right? So here is the constant term on this vector here, t dot n, right? And then over here we have this an squared times length of n squared, like that. That's what this boils down to be. Okay, so this actually simplifies quite a bit. Length of t and length of n are both 1, so these are just 1, right? So this is 1, this is 1. And t and n are orthogonal, so their dot product is 0. So this whole middle term is gone. So this winds up just being at squared plus an squared, right? So what I can do then is sort of solve for, so I have, up here I have length of a squared equals this squared plus this squared. If I solve for an, right, I get length of a squared minus at squared, right? So that may be a sort of a simpler way of going about getting an if you don't feel like getting the curvature, for example. If you don't need it, for example, this is sort of a quick and easy way to get an if you're just talking about acceleration and decomposing into components. Okay. So there's the two components of acceleration, one in the direction of tangent, one in the direction of normality. What's important to point out here is that this implies that acceleration always lies in the osculating plane. In other words, at any given point on a curve, acceleration will never take you out of the plane of your motion. It won't take you in any other direction, for example, which makes some sense. I mean, simply by accelerating, one is not changing the location or the height of one's, or the, how do I want to say this? Not the height, but the plane one is on. In other words, if you're on a flat road driving and you accelerate, it's not going to take you off the road. It's not going to lift you into the air, for example. That's not going to work with a vehicle. Unless some other force is at work. For example, you're lifting like a plane when it accelerates, but also it lifts, it comes off. There is a separate thing going on there. It's not just acceleration. It's not, if it just accelerated, the plane wouldn't take off. It wouldn't take off without some lifting force up, right? So let's talk about how this can be applied to some rudimentary driving. I've already mentioned about the acceleration taking you not out of the plane, but let's talk about a car in a turn in the road. So here's a turn, right? And say you're driving along, blah, 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 right? So car in a turn. So I don't know, should we draw the car? There's the car. So a car in a turn, what's happening here? Well, for one thing, the normal component looks like that, right? So it involves curvature and speed. If the curvature is big, and if the turn is very sharp, large curvature there, right? Large normal component, right? So curvature large normal component, i.e. If you're accelerating in a very sharp turn, there's going to be a great deal of motion normal to the curve. In other words, you're going to be going the direction of tangent, right? Perpendicular is going to be going normal. If the curve is very sharp and you're accelerating, a lot of your motion is moving perpendicular to it, okay? Additionally, this speed term is squared, so if I double my speed, for example, right, if I make my speed double, and I square that, right, I get a quadruple normal component, right? Normal component is quadrupled, right? So in either case, there's a large normal component. Think for a minute sort of logically about what happens. I mean, if you're in a turn and the turn is very sharp and you are accelerating, what happens to a passenger? They're thrown against the passenger side door of the car, right? That is the direction normal to your motion. You're going like this, right? The motion normality is maybe going like this, right? Passengers are tossed against the door, right? They're tossed like that. The same thing if you double your speed in a turn. What happens? Passenger is tossed against the door. They're moving normal to the direction of motion, right? So they are moving orthogonally, right? So this is not how to navigate a turn. Not how to navigate a turn. You don't want this. In other words, this is how you crash. I mean, if you want to go through the turn normally, you don't want to go orthogonally. Then you go off the road. This is not good. So you don't want to do that. So this is not how to navigate the turn. These are bad. So you don't want, you can't really minimize curvature. That's part of the road, but you certainly can keep your speed from doubling in the turn. That's not a good idea. So how do you do it safely? What you want, so safe turn, what you want is AT large in comparison to AN. In other words, maybe you can't get rid of AN, right? But if you're driving through the turn, you want the acceleration to be moving in the direction you're moving. In other words, that's how the car stays safely in the turn. It doesn't fly off the road, right? So you want to make your tangential component big in comparison to AN. In other words, AN can't be eliminated. The turn makes that true. But you can make AT as big as you can while keeping this AN smaller, right? So assuming curvature is fixed, and unless the road is moving as you're moving on it, it is, for a given k, in order to lower the normal component, you must lower your speed, right? In other words, nothing else will lower the normal component except for speed. It's just made up of k and v. K is fixed. Make v lower, AN gets lower, right? And so, in other words, this is very natural, right? Before you reach a turn, what do? You slow down, right? You reduce speed, reducing speed prior to the curve. So reduce speed prior to the curve, and that seems logical, right? Now what? Well, you've kind of dropped AN down, but the turn is still there. You have to get through it somewhere or another. What's the best way to do it? You want to increase AT. So to increase AT, you got to raise V prime, right? Because remember that normal component was just V prime T. Oh, I'm sorry. This is AT over here. This is AN. So this is tangential component. That's normal component. Right? So you got to raise V prime. This is the rate of change of speed, right? So let's think for a minute. Suppose that you've come up to the turn, you've slowed down, and now you're going through the turn at a constant speed. What does that actually mean? Well, if you're slow enough, probably it means you don't run off the road, but still it's not the best case scenario. So suppose that you travel at a constant speed in the turn. Well, that means that your speed is not changing. This derivative is 0. So there's absolutely no acceleration tangentially. This is not what you want, right? That means AT is 0, right? That means that all the acceleration is in the normal direction, right? So if F equals ma, right? So you have F equals ma for forces, right? All of your acceleration is moving normally. That means all the force on the car is going normally. This is not good. I mean, if you're going through a turn at a constant speed, you are always being forced in a normal direction. Sure, it's possible to get through a turn, but this is not the way to do it. This is not good. No, so this is still bad, right? Still bad. So what's a better way to do it? That's an A, bad. What is a better way to do this? Well, you've slowed down prior to the turn. You've recognized that if you go the same speed through the turn, not good. You're going always normal to the motion. What about the other alternative? Well, What if you accelerate gradually in the turn, right? So this is probably how people were taught to drive in driving school, right? You slow down prior to a turn and accelerate gradually through it, right? Why is this good? Maybe you never learned this. So if you start from a low speed, right, and you accelerate, two things happen. Number one, your length v prime, your speed derivative, is greater than 0. That means that your AT is rising. And as long as you're low and accelerating gradually, right, then your speed should stay fairly low. In other words, your speed stays fairly low. Right? This means that you get the most out of your AT while keeping your AN relatively small, right? So AT gets bigger, gets larger. AN remains not constant, but relatively constant. Right? As a consequence, the force acting on your car tends to be in the direction of motion as opposed to the direction of curvature. Over here, you don't want that. That's all the direction of curvature. That's not good. Over here, your force tends to be in the direction of motion, mainly. One more, I guess, point to consider. So I guess a lot of times people, they think that the way to handle a turn is to maybe go into it and then slow down on the turn, right? So they go into it real fast and slow down. That's also bad. So what happens when you slow down in the turn? This is still not the best case scenario, right? Well, your speed drops. That's certainly true. You're slowing down, right? Your speed drops. But it means that your rate of change of speed is negative, right? Which means AT is negative. AT is less than 0, right? So that means that you have some force acting orthogonally to you. Don't want that. That's what makes people go off the road. And actually then, if AT is negative, now you actually have force acting in the opposite direction of the direction of motion. This is not good either, right? So now you have force acting orthogonally. You have force actually pushing you backwards, essentially, going against the direction of motion. This is also bad. So I guess the take-home message here would be, if you're in a turn, the way to go is to accelerate gradually, starting from a low speed. All other possibilities lead to bad actions of forces. Okay, that's it.